using simulated FMD outbreaks in New Zealand.
Okay, so we're tackling the same sort of question that sort of William has just presented to you in a slightly different approach, and yeah, we'll show you how we went about it. So the idea was that in New Zealand, stamping out is probably our primary way of wanting to control FMD. But we know that vaccination works, but we also know that there are consequences to choosing vaccination, such as then having to deal with vaccinated animals or proving that you are free after you've eventually eradicated the disease. And so, whilst we know vaccination is valuable, we only want to use it if we believe that it's going to provide real benefit that exceeds the consequences. And so we've got this term called adaptive management, which is, okay, we start with stamping out, and at a certain point, if conditions indicate that it's going to be a large outbreak, then we switch on vaccination. So yeah, it's not we abandon stamping out and we just rely on vaccination. It's using vaccination to augment the stamping out. So in order to be able to do that, we want to know how can we predict that the outbreak's going to be large and therefore vaccination is going to be valuable. So I mentioned my plenary talk yesterday with the Quads work that we've moved to another part of the project, which is investigating a whole range of early decision indicators, or EDIs that we call them. So that part of the project, we generated like 10,000, each of our models generated 10,000 outbreaks randomly, and then we looked at the data that we had available to us, say day 7, day 14, day 21, etc., and we measured certain things that we could measure at the time, such as the number of infected premises we'd detected, the area of the outbreak, the number of spatial distinct clusters, and so on. And then we compared that to the eventual size of that particular outbreak, and we used multivariable techniques to try and evaluate the different early decision indicators. So as I said, there was quite a range of early decision indicators that we evaluated, and some of them were predictive and others not so. But then we've selected a couple of them, namely the numbers of IPs at various time points and what we call the estimated dissemination rate, which compares the number of new findings, new detections in say week 2 divided by the number of IPs detected in week 1, and you get a ratio of if it's above 1, it means we're still finding more IPs than the previous time point. If it's below 1, we know that we're starting to bring things under control. And so because they were the two that we knew we could implement within the software package that we're using. So whilst William's got the ability, I guess, your group to program and change your models very quickly, some of our software platforms are much more complex and much more difficult to program the ability to measure a whole, a much broader range of these EDIs. So we selected two that we could implement within the model as a triggering to say, okay, if these thresholds are reached in either EDR or in the numbers of IPs at various time points over the first 5 weeks of the outbreak, then we switch on vaccination. And we wanted to do that and then compare whether that was actually beneficial. So we had to set it up in a kind of an experimental plot sort of approach where we always had the trigger operating, but for some outbreaks we said, if it fires in this outbreak, we're not going to switch it on, we're going to let the outbreak proceed to conclusion. But in other ones, strategies, we would actually switch on vaccination. And then we had some other vaccination strategies where we just started it regardless of whether the trigger fired or not. So we ended up with sort of a four-way design. And let me whip through here because I've already spoken on those. So we basically, so from the 10,000 outbreaks that we sort of pre-generated and evaluated these various time points, we came up with various trigger values which were indicative of a large outbreak. So we used a 5-day estimated dissemination rate on the left there. So the blue column, the dark blue column on the very left, these are the time points. So between days 11 and 14, if our 5-day estimated dissemination rate equaled or exceeded 2, or if the cumulative number of IPs were greater than or equals to 20, we would trigger we said the trigger fired, and there was indicative that we were going to get a large outbreak. So in the trigger-based vaccination scenario, we would switch on vaccination. So there's the various time points up to day 35, and EDR values either above 2 in the early stage, because we know that by evaluating a large number of outbreaks that EDRs often do start high, but as the stamping out and so on comes into control, the EDRs drop. So we can't use, we still want to know that if we're above sort of a value that's indicative of the outbreak still relatively expanding. So those are the trigger points that we used, and if either of them, in any time period, if either the number of IPs or the EDR exceeded those values, then we switched on vaccination. So the 4 broad strategies were stamping out only, this trigger-based vaccination that we called TRV, random vaccination which always started randomly between day 11 and 35 based on a uniform sort of random distribution, and then vaccination always starting on day 21, which was 3 weeks into the response. So we wanted to see, did the trigger-based vaccination perform any better than these other vaccination strategies? Okay, so 5,000 random introductions into New Zealand. Prior to each simulation, a number of parameters were decided randomly prior to the start, and obviously we talked about which strategy we were going to apply for this particular vaccination. We had some other parameters that we were going to vary as well, so airborne spread could either be on or off for a particular simulation. The numbers of personnel resources that we had available to us, because another part of the study is really for New Zealand wanting to get a handle on what's the optimal personnel resources that we require. So we varied the numbers of personnel of different types of personnel that we had available to each simulation. So we had numbers of vets, we had a number of slaughtermen, we had administrative staff. So there was, I think, six different personnel types that we had, and we varied them. 7 was the minimum, so we would introduce a new person into the response team every day for a week, but up to 1,000. We varied the vaccination zone around, so one of the vaccination strategies, the radius would vary between 1 and 5. We also had some other variables, such as did we vaccinate smallholders or did we ignore them? We would still stamp out on them if they became infected, but vaccination-wise, did we vaccinate them not? Whether we vaccinated all farm types or just farms that had cattle, that's a question that we're interested in. The numbers of traces that a tracer could work on per day, and the number of farms that a surveillance visit could visit per day. And some of that was informed by the UK 2001 outbreak, others that we basically worked out within New Zealand. Okay, so the output of each simulation was the type of primary case. So we were randomly seeding infection into the upper part of the North Island, which is a high-risk area because of the number of large ports that we have, such as Auckland and so on. So that upper New Zealand was where we think if it's going to come in, it's probably going to come in there. We had some variables that we could measure, such as the density around the primary case. How long did it take to first detection? Obviously, we recorded, did the trigger fire or not? If it was a vaccination scenario, how many doses did we use? How many IPs did we end up with? And what was the duration? And we time-bound it to a maximum of 365 days. We did various analyses. Descriptive, univariable, multivariable analyses using both classical statistical approaches but also machine learning type approaches. And we also wanted to look at how well did the trigger actually perform. So in the stamping out only, if the trigger fired, we could then say how predictive was it of a large outbreak or a long outbreak. And we could measure the sensitivity, specificity, positive predictive values and negative predictive values. The results, okay. 13 out of the 5,000 outbreaks were never detected. So infection got seeded and it died out, didn't go on to other farms, and we didn't actually detect it, so it just died out. But there were 605 out of the 5,000, about 12%, where disease failed to spread. So we detected, well, 13 of them weren't detected, but the rest were, but there was no secondary spread. But it was highly skewed. So it was obvious to us that where the personnel resources were really constrained, like right down near 7, that we could get conditions where we end up with basically runaway epidemics that we couldn't control. So massive outbreaks that carried on right up until 365 days, where the models sort of shut off, and basically the disease became endemic in New Zealand. And interestingly, the machine learning said that if we had less than 43 vets and the trigger fired, in other words, indicative of a large outbreak, then basically stamping out with that level of resources couldn't control it. So we did end up having to exclude some of those extreme outliers because we felt that they were artificially caused by the extreme resource constraints, just so that we could analyse the data in a meaningful way. And we actually used, so if the large outbreak was bigger than either the 2001 or the 1967-68 outbreak in the UK, we said that was an extreme one, and we were going to handle those separately, but we were going to concentrate on the analysis for smaller outbreaks, because we believe that those, 2001, 1967-68 were kind of the upper limit of what we would expect in New Zealand. We think we should be able to do at least as good as the UK did in controlling them. So I won't mention that anymore, but we concentrated on if it was smaller than that, and actually the maximum number of IPs below that threshold of the UK 2001, 67-68 was actually about 700 IPs. So it was almost a dichotomous data set based on these extremely resource-constrained outbreaks. So so negative binomial regression on numbers of IPs. I don't give you all the parameter values, but basically we came up with a model that was predictive of increasing numbers of IPs based on did the trigger fire or not. So the trigger that we defined was actually quite predictive. The 4 strategies, and TRV was, so compared to the vaccination strategies compared to stamping out as the reference, the vaccination strategies did reduce the numbers of IPs, so they were protective, and actually interestingly the TRV trigger-based vaccination was 2 minutes ago was the best. Okay, so yeah, you can see those there. I'm going to have to fly. Here's the benefits of vaccination compared to stamping out, just using box plots. IPs, yeah, there wasn't a massive reduction due to vaccination, although it was marginally, if you like, significant, but we had a much bigger effect on duration for the box plots on the right. Okay, doses used, so this gave us, so the TRV-based vaccination did tend to use more doses per time we used it, but remember it was only when we were predictive of a large outbreak, whereas the other ones, they vaccinated even smaller outbreaks. So that's not unexplainable. So how well did the trigger actually perform? So this is a 2x2 contingency table. And so sensitivity of predicting a large outbreak was very, very high, so 99.3%. Specificity not so good, 66.4. Positive predictive value 0.49, and negative predictive value 0.997. So what does this tells us? That actually, if you've got we missed very few. So the one on there, the trigger negative and large outbreak results. So along the top, did it end up a large outbreak, and with the trigger fired or not? So we missed very few large outbreaks. So there was only one that was predicted to be small that actually ended up was a large outbreak. So we were very sensitive. So what it means is that we would vaccinate probably more outbreaks than maybe we needed to, but we didn't miss any that were going to be large. So it was, I think it was actually quite predictive. This is on duration, similar sort of values. Sensitivity 95.6%, specificity 0.642, positive predictive value 0.45, negative predictive value 0.979. So yeah, if we predicted it was going to be small, it actually did end up small. So I think it was quite predictive overall. And so the conclusions were that an adaptive management approach does seem to work. The TRV strategy was the optimal, if you like, for us here, and we were sensitive to detecting large outbreaks. I'm probably run out of time. Is that right, Sten? So some other findings: vaccination cattle only. Farms with cattle was no better or worse than vaccinating all farm types. I still have some questions about whether our model reflects species differences correctly, so we're going to do some more work in there. Vaccinating lifestyles, smallholders, actually was beneficial within, it reduced duration but not numbers of IPs in the multivariable models. So I need to acknowledge the Ministry for Primary Industries in New Zealand, Episoft for allowing the use of the InterSpread Plus modelling system, and Assure Quality, who provided the underlying farm denominator data set. Thank you.